that you have completed the Your Turn activities. That's 8.1.2 at the start of this video. So if you haven't done that, go ahead and pause the video here and complete those before continuing. So I've gone ahead and written down some basic answers that you can use to check your work. I'll just pause here and let you write these down. Okay, and here's the second page of Your Turn activities. So what I'd like to do is to get a sense of sequence convergence and to get a little more precise about what we mean here. And so in this next part, we'll talk about what it means for a sequence to converge for a limit. And we'll use the language of tolerances. And then I'll expect to be communicating to you both what it means for a sequence to converge using the language of tolerances and also what it means for a sequence not to converge. We'll have some examples, and then I'd like you to get a chance to practice some of these things as well. So as a first look at this material, I've written the following kind of vague statement here. But it's a good way of thinking about convergence, and it's very similar to how we think about the limit of a function as a function of x, say, as x goes to infinity. So we'll say that a sequence converges if there's some number, some limit, L, so that the sequence terms get closer and closer to L as we go further and further in the sequence. So exactly what I wrote here, the sequence Sn converges if there's a number L, which is the limit of the sequence, so that Sn gets closer and closer to L as n gets larger and larger. So let's take the example of the sequence that I've listed out here, 1, 1/4, 1/9, 1/16, and so on. Just for fun, let's review. If I want to write this sequence, and so let's go ahead and call it A sub n. And so in this particular case, we'll use A sub n, and we'll say that the nth term is equal to, well, notice that 1 is equal to 1 over 1 squared. 1/4 is equal to 1 over 2 squared. 1/9 is equal to 1 over 3 squared, and so on. So a n, we conjecture, should just be 1 over n squared. And if we look at these numbers, you can see that n squared is getting larger and larger and larger as n gets larger. And so 1 over a larger and larger number is really approaching 0. So we would like to say that this sequence converges to 0. And so what I'd like to do is introduce tolerances to talk about this. Now, in the last part, when you were working on the Your Turn exercises, I talked about using the language of functions and what we know about limits of functions. What you would do in this scenario, and this will not be with tolerance language, but I'm going to go ahead and do a little aside here. For you, note that the limit as x goes to infinity, if we think about the function 1 over x squared, that this limit is equal to 0. And so that's kind of a guiding principle here. Notice that this function is really going to be equal to the sequence terms whenever n is an integer, and so therefore we can say that the limit of the sequence ought to be the same as the limit of the function, which is defined on all possible x's. So we already have that intuition, but let's use this language of tolerances because it's going to be a little, it's going to apply to other types of sequences as well, and it's a good graphical interpretation of what's happening here. So this tolerance language, what we're saying is what I've written right here. Okay. So if we start with a tolerance, and you think about your tolerance as being some small number, what you'd like to do is place a collar around the limit. So you'd like to create some region above and below the limit, and then the idea is that given that tolerance, eventually our sequence must always be within the tolerance of the limit. Okay, and so what I have here is a graph. In this particular case, I have a graph of our sequence from above. A sub n is equal to 1 over n squared. And I've got a graph with a tolerance of 0.1. And you can see that the terms start out outside of this collar, but eventually they go into the collar. So let me go ahead just and highlight how that's happening. So you can see that the terms eventually are all going to stay within that collar. So the idea here is that that with these tolerances, we must be able to find some point at which the sequence always will stay within the collar, and we must be able to do that no matter what the tolerance is. So in other words, I had here a tolerance of 0.1. I need to be able to shrink that tolerance, and eventually I may have to wait longer. Eventually the sequence will fall within that tolerance. Okay, so let me go to Desmos and show you that. So at the top of the next page is a link. You can see it right down here at the bottom of the screen that I'm recording. So we'll just go to that, and see, I think I have it up in Chrome in this tab here. So I have graphed the sequence 1 over, and let me just not make this 100, let me make this 10. Okay, and I've got the sequence x squared. Okay, and so you can see what's happening here. Let me make the tolerance in this case. Let's see what was going on in my last graph here. I had a tolerance of 0.1, and you can see that already once I hit n equals 4, I'm staying within that tolerance. So let's go back here and take a look. You can see that there's n equals 3. By the time I get to n equals 4, I'm already within the tolerance. And so here 1 is way outside. By the time we hit 4, we're well within the tolerance here. If I stretch this out a little more, it will look a little bit more like the graph that you see on the handout. So we can see that that in this case, right, if I plot more and more points here, now I want to shrink this, we can really see that the points do all lie within my epsilon collar here. And in fact, the n that we would need to use here is n equals 4 for this particular tolerance. Now, if I was to select a smaller value here, let me make 0.1 the top step size. Right, if I was to make my tolerance even smaller, right, what you can see is that as I shrink my tolerance down, now my points don't lie in the collar anymore. So according to my definition of sequence convergence, what I need is to be able to find a point in the sequence after which my points all lie in this color. So what we'll need to do then is we'll need to increase n. So now let's make n larger. And so what you'll see here is that if I make my n larger, right, eventually out here you can see that when we get past, say, 27, 26, see if I can shrink this way. Whoops. Okay, so I guess working with these windows is a little bit challenging here, but when we're out here, here you can see, and I think what I saw was that, in fact, if we zoomed in kind of close to between maybe in the 20s, what we would see is that the function enters this tolerance out here. 23 is still within the tolerance. Let's check 22. All right, 22 is not in the tolerance, but if we scroll over here to 23, we find that 23 and all the numbers bigger than it are in our new tolerance here, 0.002. So let's get out to 23 and we'll take a look. I'm scrolling over here and you can see that A of 23 is small enough so that we're within this new tolerance of 0.002. So in fact, just visually you can see that because the terms of this sequence are getting tinier and tinier and tinier, the limit is in fact 0. And how do we make that precise? We can say that for any tolerance we set, no matter how small, we can always go far enough out in the sequence that the remainder of the sequence lies within this tolerance of whatever our limit is. Okay, and so here I'm just giving you another example of the function a sub n, or the sequence where the nth term is 1 plus sine of n over n. And you can see that those terms are oscillating, but they seem to be oscillating around 1. And in fact, if you plot those terms and you pick any tolerance, if you shrink the tolerance even further, you can get the entire sequence to lie in a collar around 1 of any width that you like, as long as you go far enough out in the sequence. Right. So pictorially, right, what we have is, let me go ahead and just draw a picture here, is that if you have some limit L, right, so let me just go ahead and draw that in, then right, we can make our collar up and down here. So this is the tolerance. And this is also the tolerance. Right, and so it must be true so if the limit of the sequence S sub n, as n goes to infinity, if this is equal to L, then for any tolerance, okay, and so our tolerances have to be positive numbers. So for any tolerance greater than 0, then there must be some position after which, all right, and so here my position, I'm just going to call it n, I'm going to call it n star here, after which the sequence lies entirely within the collar. Right. And so the sequence can do whatever it wants to outside of the, so I'm just going to plot some points here. It can do whatever it wants to outside of the in the initial part of the sequence, but eventually it must always, all of the terms must eventually stay within the collar, right? If the sequence always popped out of the collar, no matter if there was some collar where the sequence would always pop out of the collar, then the sequence would not converge. So what I'd like to do is give you some time to try working with this tolerance code. So we'll go ahead and pause this video, and we'll start up the next one with a discussion of this particular tolerance activity, and I'd like you to compare it to what we did with this sequence 1 over n squared. So we'll begin there, and then we'll continue with a formal definition of convergence from your textbook, and then discussing how you can show that a sequence does not converge to any limit. Okay.